Okay, good morning. Today I'll start the topic steam turbine, but some calculations. Previous lecture also we have done some calculation. Today also we'll do some calculation. Let's recap little bit. So Rankine cycle is started. Okay, Rankine cycle will have one boiler. Boiler will be giving superheated steam to turbine. Okay, turbine I am drawing in specific way. You should not draw in opposite way. I already told. So if you are drawing like this, so it is okay. But if you are drawing in opposite way like this, it is wrong. Okay. So this will be compressor. Later we'll discuss about compressor. Now this turbine output will be going to one condenser. So condenser purpose is to release heat. Okay, and boiler purpose is to give heat to water. So Q1, and there will be one pump. Actually pump will be working in the liquid zone. So pump normally we draw like this. Okay, and if I draw in TS diagram, it will be first you have to draw vapor envelope, then in boiler, this is boiler, so you have to put the number properly. Okay, already you have seen. It can be inside, outside, everywhere possible, but ideally we will be assuming this after boiler, let's say 1, 2, 3, 4. Okay, 1 to 2 is your condenser, 2 to 3 your pump, 3 to 4 your boiler. So 3 to 4 boiler is adding heat to fluid. So first your sensible heating, then phase change will be occurring, then last part will be your superheating. After superheating, your turbine will be working. So turbine will be extracting energy, power will be extracted, power extraction. Okay, so turbine is giving power, and turbine ideally we are assuming this is isentropic process. Okay, ideally isentropic, but practically if we consider, then it will be like this. So 1 dash and 2 2 1 1 dash is constant pressure line. Okay, 4 2 1 dash, it is irreversible process. That's why we are putting dotted lines, irreversible process, and energy will be lost. So we expected energy 4 to 1, but actually we are getting 4 to 1 dash. So we are getting little bit lower amount of energy. But same thing is happening in pump side. 2 to 3 is your ideal case, but practically it will be like 3 dash. Okay, so 2 to 3 ideal process, but 2 to 3 dash is practical or actual process. Actual process. Okay, so what is happening, 2 to 3 dash, you see lines longer means you are giving actually more energy. Pump will be taking more energy than whatever you calculated for ideal case. In turbine you are getting little bit less energy, so actual cycle actually will be giving little bit lower energy whatever you are calculating. Okay, but first you have to assume everything ideal and you have to calculate, and we are assuming also for ideal case that there is no heat transfer in other pipeline, in other places. Okay, all the heat whatever boiler is giving, turbine is getting the same amount of heat. Okay, and some amount they are extracting and some amount is going to condenser. So condenser purpose is to release only heat, so it is not giving any other pressure drop or pressure increase. Okay, it is only changing phase and releasing heat. In boiler, phase change occurring and increasing pressure. Now this is simple Rankine cycle. Simple, I can say simple Rankine cycle, but we discuss regenerative reheat also. Reheat, like I have one turbine, I have boiler. So from turbine, steam will be going to boiler, it will be reheated again it will be going to another turbine. Okay, so turbine 1, turbine 2, then it is going to your condenser, then condenser to pump, pump to boiler. So you are taking 2 times energy, but you are having condenser 1 time, means you are releasing less amount of heat actually. Okay, so you improving performance of your system. So maybe 2-3 stages possible. And another is regenerative system. Regenerative system, what you do, you have turbine, then you have boiler. Now turbine will have condenser. After turbine, okay, condenser, then there will be pump, then boiler, it will go. So after pump, actually water temperature is lower. Now what they do, they will take some amount of steam and they will be giving here. Okay, then you are pumping to boiler. So this is bleed, they call bleeding. Okay, some small amount of steam they will take and that will be put after pump. Okay, so the temperature will be going up. So boiler will be giving less amount of heat because already you got some heat from your turbine. Okay, so this is called regenerative system, and this is called reheat system. So you may have complex regenerative plus reheating system also. Okay, so if I have regenerative and reheat, how it will look like? Regenerative. Okay, now regenerative plus reheat system we have, then how it will look like? So I have one boiler first. Draw this boiler. Okay, from boiler it will go to turbine 1. Okay, so turbine 1 will be giving power. So boiler is giving this much of energy to this turbine 1. Then turbine 1, some after turbine 1, the steam will be going back to boiler again to get reheated. It will move to another turbine. Okay, turbine can be on same shaft because you have different many shafts, then controlling power will be difficult. So normally they will be attached on the same shaft and they will be managing. Okay, so then it will be giving exhaust steam. It will go to boiler again, so it is getting reheated. So reheating is happening. Reheating. Okay, then reheating steam coming to another turbine, turbine 1, turbine 2. Then turbine 2 steam will be going to your condenser. Okay, so turbine 1 steam did not go to condenser, rather it went to boiler. So from boiler it went to turbine 2, turbine 2 to condenser it is coming, condenser to again pump. Okay, so pump, then what is happening, you take some amount of steam as a bleeding steam, then you mix here. Okay, this is regenerative part. Okay, so bleeding is happening. Then again you put another pump, then here also you take small bleeding amount, you mix it here, again pump, then you put in boiler. Okay, so you see this several steps are happening here. So I can put numbering here. Number they have put like 1 here, 2 after pump, then 3, then after pump 4, then mixture 5. Okay, this after pump they did not put any pump actually here, so we can remove it. Okay, we can put pump also, or we may ignore also. Now this is 6, this is 7, this is 8, this is 9, and this one A, this one B. So now draw the TS diagram. So TS diagram, when you are drawing, first you draw the vapor envelope. Okay, now you draw, you see 5 to 6, 5 after, before boiler and after boiler you see. So 5 means you have to come here, 5 to 6 here, 6 to 7, 6 to 7 happening like this, 6 and after turbine, so 7, 7, then 7 to 8, 8 again increasing temperature, again going down, 8 to 9. Okay, so after 9 it is going to 1. Okay, you see these points 5 to 6. So the after 5 is after 5 the line is crossing and touching the saturation line, so we will not put any number because only it is within boiler, so we are not putting any number. Now 2 to 3, 2 to 3 is 1 to 2 is pump, 1 to 2 is pump. Then 2 to 3, what is happening? 2 to 3, 2 to 3 actually heat increasing. So 2 to 3 is like this. You are taking bleeding amount B, 2, 3, then 3 to 4. 3 to 4 you see pump again working. So 4 to 5. So 4 to 5 pump increasing temp. 3 to 4, 3 to 4, 4 to 5. Okay, so you see 4 to 5, where is 4? 4 after pump, then 5, 5 before 5 on mixing is happening. So this is mixing point. Then 4 to boiler is increasing temperature 5 to 6. Okay, and A is here. I think A is here. From here, A I'll put here. A is here. Okay, because this is 7, this point, otherwise there will be confusion. This is B point. Okay, this is 6, 7, 8, 9, 9 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. So this way you can draw the TS diagram. Okay, this is very complex actually. So every turbine is giving some bleeding steam to increase temperature of feed water. Feed water means the water going to boiler, from condenser to boiler. When you are supplying that steam, so you are increasing temperature using your bleeding steam. Okay, so whenever you are drawing this sort of diagram, you just put proper arrow diagram, proper numbering, matching numbering left side and right side. Whatever line diagram I have drawn, whatever TS diagram is there, the numbers must be matching. If there is any mistake in number, then you will not get number marks. So we'll go to the problem 4. The value of enthalpy of steam at inlet and outlet steam turbine in a Rankine cycle 2800 and 1800 kilojoule per kg. Neglecting pump work, so they are asking to neglect pump work. So first you draw steam cycle TS diagram, right? So 1, 2, 3, 4. So I am giving number randomly. Sometime I am starting 1 after boiler, sometime before boiler. So you can use your own notation. There is no specific hard and fixed rule, but everything must be correct, whatever notation you use. Okay, so H1 is given 2800 kilojoule per kg and H2 is given 1800 kilojoule per kg. Steam rate or specific steam consumption, specific steam consumption equals 3600. You can see okay, 3600 divided by WT minus WP. So specific steam consumption 3600, WT minus WP. WT means this turbine work, WP is your pump work. So 36 is coming for your time change. Now pump work, WP equals 0. It is given that we have to neglect the pump work. Now steam rate equals 3600 divided by WT, because WP is 0. So it is coming 3600, and turbine work H1 minus H2. So this is giving 3.6 kg per kilowatt hour. Okay, so we'll see next problem. So this is from GATE exam. One problem was there, not in your marine engineering, other it was mechanical engineering GATE problem. So steam power plant operating Rankine cycle, steam enters turbine 4 MPa at 350 degrees centigrade. Okay, in steam power plant operating on the Rankine cycle, steam enters turbine at 4 MPa, 350 degrees centigrade, and exits at a pressure 15 kPa. So first you have to draw your steam cycle. So TS diagram. Draw steam cycle here, pump here, it is here. So again numbering, you put your own numbering, 2, 3, 4. You put arrow symbol, TS diagram. Okay, now P1 is given 4 MPa, they are saying 4 MPa steam entering the turbine. So P1, this actually 4 to 1, you see this same constant pressure line. Okay, inside boiler pressure will not be changing, it will be fixed within the boiler. Okay, so this is 4 into 10 power 6 Pascal. So temperature 350 degree centigrade is given. So 623 K, 273 plus 350, it will be coming 623. P2 equals 15 kPa. So 15 into 10 power 3 Pascal. Now adiabatic efficiency also given. You can read the problem. The adiabatic efficiency is 90%. Eta adiabatic 90% is given. The thermodynamic states of water steam table, actually small steam table is given here instead of giving full steam table. So from there you can select the data and you can calculate. So H specific enthalpy, S entropy, and N is the specific volume. Okay, small n they are using for specific volume. So we have to calculate net work output and heat supplied. Okay, so from this steam table you are getting H1 equals 3092.5 kJ per kg. Okay, this one, and H3, because you see this 4 MPa and 350 degree centigrade temperature it is there, so you are getting this one. So H3 means this condition in TS diagram you see 3.3. So this value is coming 225.94 kJ per kg, or you can say this one H fluid. Okay, and Hg equals 2599.1 kJ per kg. Okay. S1 equals S2 because entropy constant, S1 and S2 entropy same, and SF plus X Sg minus Sf. So it is coming from dryness fraction. Now X equals S2 minus Sf divided by Sg minus Sf. This is giving 6.5821 minus 0.7594, 8.0058 minus 0.7549. So this is given 0.8033. So now H2 equals HF, again the same formula coming, X Hg minus HF. This is phase change occurring, so that's why Hg minus HF is coming. Hg will be having more energy because phase change occurred. HF means fluid will have less energy. So H2 value will be coming like this, 225.94 plus 0.8033, it is coming from here, 25599.1 minus 225.94. So this value will be coming 2132.3 kJ per kg. Now theoretical turbine work. Theoretical turbine work equals Wt equals H1 minus H2. If actually you should have your TS diagram every time in front of you. Okay, and we started this one 1 2 3 4. Okay, so I am getting H1 minus H2 W turbine work. So it is giving 3092.5 minus 2132.3. So this is giving 960.2 kJ per kg. Now actual work done by the turbine. So theoretical work into theoretical work cross 0.9. Actually here some energy is lost because we are assuming theoretical means ideal one, and practically we are getting a little bit less. So 90% we are assuming we are getting. That's why 0.9 is coming, and this is giving the problem actually. Adiabatic efficiency given 90%. So actually we can harness, actually we can get 90% power from turbine. Okay, so 864.18 kJ per kg. This is coming from this 960.2 into 0.9. So this is giving 864 kJ per kg. Now pump work. WP equals NF P1 minus P2. So specific volume is given actually. So 0.001014, and P1 P2 you can get from the table. So it is coming 40 minus 15. So it is coming 4.04 kJ per kg. So W net work we are getting WT minus WP 864.18 minus 4.04. So it is giving 860.14 kJ per kg. So heat supplied equals, again TS diagram you have to draw. TS 1 2 3 4. Okay, so heat supplied means 4 to 1. So H1 minus H4, because H1 will have more energy than H4. Okay, so from pump work WP equals H4 minus H3. You can see this pump work H4 minus H3. This is 4. Now H4 equals WP plus H3 equals 4.04 plus 225.94. So this is giving 229.98 kJ per kg. Now heat supplied equals Q equals H1 minus H2 why H1 minus H2 H4 H1 minus H4. So H1 is 3092.50 minus H4 is 229.98. So this is giving 2863 kJ per kg. Okay, now if I give mass flow rate, then actually you can get total energy, how much you are supplying or how much you are getting, because mass flow is not given. So that's why we are calculating based on per kg of mass or steam. Okay, so yeah, so another problem is there, a little bit different. A coal fired steam power plant. So it may be, for example, your steam system in your marine boiler heating purpose. So that can be coal fired, that can be liquid fuel fire. So coal fired maximum coal fired systems are replaced actually. These days diesel based systems are coming up. So basically maximum steam turbines are replaced already. Okay, let's assume it is still coal fire is there. So coal fired steam power plant operating on a simple ideal Rankine cycle. So first Rankine cycle when I am talking, so TS diagram, okay, and your envelope. Now and produce 300 megawatt electric power. So how much electric power it is producing, it is given. Turbine inlet pressure and temperature is given. Inlet pressure and temperature is given. Okay, so again numbering here 1 2 3 4, you can see again I am changing the numbering, and this pressure is given because 2 to 3 pressure is same, so this pressure is given 5 MPa. Okay, and pressure temperature also given 450 degrees centigrade for point turbine inlet pressure, that means T3 is given, temperature at 3 is given, maximum temperature. The consider pressure 25 kPa, condenser pressure. So this pressure, this is 1, okay, so this 1 to 4, maybe 4, I can say, yes, I can put x. So 1 4 x, this is actually constant pressure line, constant pressure. Okay, so pressure is given 25 kPa, 25 kPa, this one, and the coal use has heating value HCV, coal heating value. So I can write C heating value HV coal. Okay, heating value of coal is given 29.3 megajoule per kg, and 75% coal energy is transferred to steam, 75% goes to steam, so some energy lost. Okay, because flue gas will take 25%, only 75% energy going to steam. Okay, the electric generator has an efficiency 96%, so electric generator you are using, that is having 96% efficiency. Okay, so you have to use the data enthalpy turbine inlet. So H3 is given, enthalpy condenser inlet means H4 is given, enthalpy condenser exit H1 is given, enthalpy boiler inlet H2 is given. Determine overall plant efficiency, required rate of coal supply. Okay, so eta overall equals eta combustion efficiency. Combustion efficiency is the 75%, and eta thermal efficiency, eta thermal into eta generator efficiency. So overall efficiency means like how much total fuel to your electric supply, that much of power. So combustion is having certain losses, your thermal efficiency some losses in turbine, and your generator also having some losses. So all losses you are multiplying, then you are getting overall efficiency. Now combustion efficiency given 75%, generator efficiency 96%, but thermal efficiency not given. So thermal efficiency how to calculate? So thermal efficiency actually you will get from turbine power and divide by your heat supplied in the boiler. Okay, so 1 minus H4 minus H1, H3 minus H2. If we put all the values, 1 minus H4 is given 2277.36 minus H1 is given 271.96 divided by H3 minus H4, H3 3317 minus 2 H4 2277.36. so this is giving value 0.34%. so 34% efficiency you are getting, thermal efficiency. Now overall efficiency, eta overall, so you multiply all the terms, 0.75 into 0.34 into 0.96, so this will be giving 24.5%. so you see so low efficiency you get because of so many losses will be there, so you are getting only 25%. There will be many other losses also, so actual efficiency will be further lower. Okay, because piping loss and other losses also not considered. Okay, now next part is there, how much coal is supplied. M dot coal supplied, electric power output divided by HV coal, heating value of coal, into eta overall efficiency. Overall, So electric power output is given in your data. So it's giving 30 megajoule, 300 megajoule, 330 kilojoule per second. Okay, and your heating value is given 29300 kJ per kg coal into your overall efficiency. We already calculated 24.5. so this is giving 41.97 kg coal per second. Okay, so this is your answer.